The absolute value function is for measuring distance. My first exposure to the absolute value function was as a conditional operation without any motivation. It went something like this. If x is greater than or equal to 0, then the absolute value does nothing. If x is negative, then the absolute value makes it positive by multiplying by -1. For example, the absolute value of -3 is 3. So what's the distance between 3 and 7 then? Well, if I put a rock at 0 on the number line and a pine cone 3 bricks to the right of 0, and another pine cone 7 bricks to the right of 0, then the distance between the two pine cones is the number of bricks between them. Since 7 is 4 more units way to the right of 0 than 3 is, then the distance is 4. And so the distance then between -3 and 7, in the same way I could put a pine cone 3 units to the left of 0. So the distance between the two pine cones now is the total number of bricks in between the two pine cones. This can be found by subtraction if you remember that subtracting a negative number is just like addition. The absolute value function really allows you to compute distances without having to think carefully about the relative position of each point on the number line. So what's the distance between -3 and -7? Well, to calculate the distance between -3 and -7, I can do this in one of two ways. On one hand, I would take -3 minus -7 and then take the absolute value of that. Since -3 plus 7 is 4, the absolute value of 4 is 4, the distance is 4. On the other hand, if I had subtracted in the opposite order, -7 minus -3, that simplifies to -7 plus 3, and since the absolute value of -4 is 4, I get the same distance. This is just like you would expect on the number line. So the distance between -3, 3 bricks to the left of the rock, and -7, which is 7 bricks to the left of the rock, that distance is also 4. Now to solve for solutions. When you're reading an absolute value equation, it's best to state it in terms of distance. In this particular case, we're trying to find all the points on the number line that are at a distance of 4 from 3. So if you locate 3 on the number line, you're looking for points that are at a distance of 4 from 3, it stands to reason that you can only go in one of two directions, to the right or to the left. You measure off 4 bricks to the right of the rock and 4 bricks to the left of the rock, and you can see that there's pine cones at 7 and at -1. Avoid sloppy algebra. This is an interesting example where sometimes 2 wrongs can make a right. Ultimately, my point is that although this might give you the correct solution sometimes, it won't always give you the correct solution. So the example I have in mind is where x minus 3 squared equals 16. Some people would say that the square root of x minus 3 squared is x minus 3. Unfortunately, that's not true. I'll explain why in a moment. A lot of people will also convince themselves that the square root of 16 is plus or minus 4. That's also not true, since there's a reason why the square root function is called a function. But if you put these two pieces together, you get an equation which actually is true. In fact, the square root of x squared is not x. So notice that the square root of x squared sometimes is equal to x, but only when x is greater than or equal to 0. However, when x is a negative number, the square root of x squared is not equal to x. In fact, the square root of x squared makes x positive. So in general, I'd say that the square root of x squared is absolute value of x for all values of x. square root of x squared is absolute value x. So an accurate solution is a reliable solution. So I want to demonstrate how to solve this quadratic equation using square roots. You take the square root of both sides. The left-hand side becomes the absolute value of x minus 3. The right-hand side becomes 4. And so now I'm just looking for a point on the number line whose distance from 3 is exactly 4. There's only two ways I can go, to the right or to the left. To the right I get 7, to the left I get negative 1. So x equals negative 1 or 7. Solving for solutions. Here's another example of an inequality. Solving an inequality. Just like before, you can take the square root of both sides. The left-hand side becomes absolute value x minus 3, right-hand side is 4. Now I'm looking for points whose distance from 3 is less than or equal to 4. That is to say, x needs to be within 4 units of 3. So since the rock is at 3, any points that are at a distance of less than or equal to 4, that means that there are all those pine cones that are close to 3. They're between negative 1 and 7, including all the spaces in between the pine cones. So I can represent those points with an interval, and it can be expressed as all x's between negative 1 and 7 inclusive. Another example of solving for solutions. If x plus 3 squared is greater than 16, again you can take the square root of both sides. You get the absolute value of x plus 3 is greater than 4. That means that the distance away from not 3 but negative 3, remember the absolute value of a difference is distance only if it's a difference. So with respect to the point negative 3 on the number line, I can measure off a distance of plus or minus 4, and that'll give me 2 points on the number line that are exactly 4 units from negative 3. I'm looking for the values of x's that are beyond 4 units from negative 3. That is to say, they're further away from negative 3. So since negative 3 is 3 units to the left of 0, I can measure off a distance of plus or minus 4. And I'm looking for all those points that are at a distance of greater than 4 from negative 3. That's going to correspond to pine cones that go beyond, either to the right or to the left of these two pine cones. If I had more pine cones, I would keep indicating that the points keep going to the right and to the left, as well as the spaces in between those pine cones. Since it's a strict inequality, we will not include 1 in negative 7. And in conclusion, x is less than negative 7 or greater than 1. Here's some more for you to try. See if you can use the same principles interpreting each of these equations as distances.